Today we begin our process of undoing derivatives. In other words, imagine we're given a derivative and we want the original function. We need a way to undo that derivative. Just like we undo addition and subtraction, multiplication, division, and all other types of equations, we have a way to undo the derivative, and it's called integration. The reason we've developed derivatives is so we can find things like rates of change, slope of the tangent line, marginal cost. But if we have those things, the marginal cost, the marginal profit, and we want to find the original cost or profit function, we have to undo that derivative by integration. The first thing we're going to do is define what's called the antiderivative. The antiderivative exists, we say, if f and little f are two functions, and if the derivative of big F is equal to f of x for all x in the domain of the function, then we say that big F is the antiderivative of f of x. How do we show this? Well, I have the integration rules here for you that we'll get back to in just a minute, but let's look at this first example here where we're going to show that f of x equal to x cubed plus x squared plus 50 and g of x equal to x cubed plus x squared minus 80 are both the antiderivative of f of x. To show something is the antiderivative, we want to show that this is the derivative of the actual function. So if we take f of x and we take the derivative of that, we get 3x squared plus 2x plus 0, which is this function here. And based on our definition, since f prime of x is equal to little f of x, then big F is the antiderivative of f of x. Notice likewise, if we take the derivative of big G of x, which is x cubed plus x squared minus 80, the derivative of that is 3x squared plus 2x. Again, they are both an antiderivative. So how do we know which one we're concerned about? Well, we're going to get to that a little bit later, but first, how do we create these antiderivatives? How do we do these integrals? If we have the integral of a constant, the value is simply kx plus c. And this represents this unknown value that we're not sure which antiderivative we're talking about. Likewise, if we have an exponent, we're going to raise that exponent by 1 and divide by that, sort of undoing when we pulled that exponent out front. The integral of 1 over x is ln of x, and the derivative of e to the x is e to the x plus c. So let's practice these. Notice here, this is going to apply to rule 2. When we take the integral, we raise our exponent by 1 power, and then divide by that same exponent plus c. We don't know what that c is yet, but we'll learn how to find it later. This gives us a value of x to the 6 over 2 when we reduce that fraction plus c. When we have multiple parts to a polynomial like this, we integrate each one separately. This gives us a value of 6t to the 6 over 6 minus 4t to the 4th over 4 plus 10t cubed over 3 plus, don't forget, this is not 0. We're not taking the derivative, we're taking the integral, so it becomes plus t plus c. All of these are then reduced. We're left with t to the 6th minus t to the 4th plus 10t cubed over 3 plus t plus c. Note, to check these, we can take the derivative of this new function that we found and make sure that we get back to our original function. Here, this fits our third rule, and we know that the integral of 5 over x is ln of x, and that 5 remains out front, plus c. When we have something like this where we're dealing with a square root, just like when we took derivatives, it's sometimes easier if we write this as an exponent, y to the negative 1/2, and then we follow the same rules. We're going to add 1, which gives us a positive 1/2, and then we're going to divide by that same exponent, which can be flipped and turned to multiplication to give us 2y to the 1/2 plus c. This third one, we do the same steps that we have previously, treating each one separately. The integral of e to the x is e to the x. The integral of x to the 2/5 is going to be x to the 7/5 because we add 1 divided by 7/5 plus 3x. When we simplify, this results in e to the x minus 5/7 x to the 7/5 plus 3x, and don't forget that plus c. Here, if we separate each piece here, we end up with t cubed over t squared plus t over t squared plus 1 over t squared dt. And we integrate each of these. But first, if we simplify, we get t plus 1 over t plus t to the negative 2, just to bring it up top. And then integrating each of those, we get t squared over 2 plus the ln of t. And then we're going to get plus t to the negative 1 over negative 1. And we can simplify this to t squared over 2 plus the ln of t minus 1 over t plus c. Let's look now at number 8. Here's where we're actually going to find a c value. We're given the information that f prime of x, in this case, is equal to x minus 1 over x, and we know that f of 1 is equal to 3/2. Notice that this is f, not f prime. To find the actual function of f, we're going to integrate both sides here. When we integrate the derivative, we end up with the original function, and then integrating each term here, we get x squared over 2 minus the ln of x plus c. We can now determine our c value, though, using this information. So we have 3/2 as our value of our function is equal to 1 squared over 2, because we're given a value of x, minus the ln of 1 plus c. The ln of 1 is 0, so this disappears. And when we subtract 1/2 from both sides, we get c has a value of 1. So our function ends up to be x squared over 2 minus the ln of x plus 1. This comes in handy when we're dealing with real-world problems. For example, here, we know the marginal cost is given by the following function. You have to know that marginal cost is actually the derivative of the cost function. In order to find the actual cost function, we'll simply integrate both sides, resulting in c of x is equal to 3x squared over 2 plus 4x plus some constant. But we're told in this case that the fixed cost is 5,000, which can be translated into 0 items is a cost of 5,000. And so we end up with a final equation of 3x squared plus 2 plus 4x plus 5,000. It's important to know these terms like marginal cost, marginal revenue. The last one we're going to do together, and I'll leave these others to you as an exercise, is let's consider this one with profit. We have a marginal profit function, so we have p prime is equal to 120 plus 3x. If I want to find the profit function, I'll integrate both sides, which gives me p of x is equal to 120x plus 3x squared over 2 plus c. Now to find this c value, I've been given some information here. I know that if I sell 30 speakers, I make a profit of $1,200. So when I plug in those two values, I have 1,200 is equal to 120 times 30 plus 3 times 30 squared over 2 plus c. Solving that for c, you're actually going to get a c value of negative 3,750. We can then write our actual profit equation to be 120x plus 3x squared over 2 minus 3,750. And then in part B, if we want to know the profit from 40 speakers, all we have to do is plug in our 40 for our x value. giving us a value of $3,450 when we sell 40 speakers.